All right, welcome everybody. Today we're going to talk about lesson number 57. This is day 2 of verifying trig identities. And the truth is, the goal is still the same as it was during day 1. You are still trying to do what's highlighted here in yellow, which is to prove, show, or verify each of the following trig identities. Remember, I'm only going to ask you to do this for problems that are 100% true. So as long as you can get the left-hand side equal to the right-hand side, then fingers crossed that you did legal algebra along the way. Notice here in green, I have for you homework 57 problems listed. So just make sure you go ahead and jot those down. I didn't make you a worksheet for today since it's only 3 problems. I figured you could just as easily copy those in your notebook. Before we go ahead and do those, and again, the whole point of having a day 2 is really just for a couple of reminders, a couple of things to watch out for, those common errors, and then just to see a couple more of the harder algebraic techniques in action. The first thing you just might want to remind yourself, so you've been writing a whole bunch of sine squareds and cosine squareds, and I just want to make it clear, when you say cosine squared of x, what that means is you're taking the cosine of x and you're actually squaring it. So I just want to make sure that you know that those two statements are equivalent. What it is absolutely not equal to is the cosine of x squared. So maybe draw a big red X through that just so you don't get confused. The two purple things are equivalent, but the red thing is not. So just be careful. Again, when it comes to these problems, we tend to write it as this version. When it comes to later in the chapter, we tend to write it as this version. But again, this version is not equivalent. So just don't get confused and think that it is. Additionally, a cosine squared, if it was valuable to you, you could rewrite that as a cosine times a cosine. Now, for some reason, if I was to give you cosine times cosine, people seem to have no trouble multiplying those out and getting cosine squared. Where the trouble does come in is if I give you a cosine squared, for some reason, people are either reluctant to rewrite it as cosine times cosine, or maybe they just don't realize it. But I do want you to realize that there's value in going both ways. Similarly, let's say that you had cosine cubed of x. You could write that, if it was helpful, as cosine squared of x times the cosine of x. And again, if I was to give you this right-hand side, you likely would have no trouble multiplying those to be cosine cubed. What you're less likely to be able to do, or just to remember that you're allowed to, is to break up the cubed into a squared and a first power. So just make sure that you do know it's legal to do it both ways. And the main reason why you might want to start with the left side and turn it into the right side is if you're trying to reduce the powers. So if you have a high exponent and you would like it to be smaller, that's a good idea to you that you should perhaps break it up. So just kind of something to keep in mind as we progress here. Let's go ahead and take a look here at number 1. You're trying to prove the left-hand side is equal to the right side. The truth is that both of those sides don't look great, but I think the left side is going to have a little bit more to do. When it comes to the left side, we're going to go ahead and try to factor. Again, one clue that factoring is the way to go here is you're trying to take the addition and subtraction from the left side, subtraction, and you're trying to turn it into a multiplication. The only way that you can do that is factoring. So you're going to factor the GCF out of both of those pairs. So if you have sine to the 1/2 power and then sine to the 5/2 power, the largest that you can take out is sine to the 1/2 power of x. And then you can take a cosine out of both. Remember, you're factoring the greatest common factor out of each term, and terms are separated by pluses and minus. So now, taking a look at this first term, if you took out the sine to the 1/2 and you took out the cosine, you took out everything and you're just left with a 1. Then it's a minus. If you took out sine to the 1/2 away from sine to the 5/2, you would be subtracting those. So 5/2 minus 1/2 is how you know you're left with sine to the 4/2 x. And then you took out the cosine, so that's all you're left with. Obviously, that looks a little strange, so hopefully you would then further realize that this is sine to the 1/2 power of x times the cosine of x, and then this is really just 1 minus, if you simplify 4 over 2, that is, of course, equal to sine squared. If you look at the right-hand side, remember, don't ever forget where it is you're headed. Well, you have a 1/2 power and you have a square root, so those are, of course, equivalent. Then notice you only have a single cosine so far on the left, and you'd like there to be to the 3rd power. That's a clue to you that we need more cosines. Where are those cosines going to come from? Well, hopefully by this point, if you see 1 minus sine squared, bells and whistles start going off, and you say to yourself, hey, that's a cosine squared. And then don't forget, you have sine to the 1/2 x times a cosine. And again, when you're doing these problems, if you get to a spot where you're like, I've done everything that is obvious, how do I get to the end? A lot of the times it means you're actually done, and that's what it means in this case. So if you look carefully, this cosine to the first times cosine squared, that is of course equal, if you multiply them, to cosine cubed of x. And then just like I had reviewed for you over here on the right-hand side, sine to the 1/2 power of x, that is really equivalent to the sine of x to the 1/2 power, which means you can write that as the square root of the sine of x. So all that work, you're done. Again, do something to let me know that you're done. I tend to box my answer and then write those little 2 lines there, but you can do kind of whatever works for you. And of course, as long as you have the left-hand side equal to the right-hand side, that is the goal. Notice I did, of course, change the order, which is perfectly legal as long as it's multiplication. So a little bit of new stuff there with the fractional exponent, but the factoring and the replacement and the rearranging, that's all stuff we've been doing for a couple of days now. On to number 2, you're trying to take that big old messy fraction and turn it into a nice simple secant. If you're trying to turn some big messy problem into a simple secant, that means lots of things have to cancel. If lots of things have to cancel and you have a big old fraction, that usually means that things are going to get messier before they get nicer. So might be hard to see here, but the thing that the secant most has in common with the rest of the problem is a cosine. So I'm going to go ahead and on the numerator, I'm going to go ahead and rewrite that secant as a 1 over a cosine minus 1 over 1. Again, that is just my numerator. Then here's my big fraction bar. Then my denominator is going to be just 1 minus cosine. Then the bottom is 1 minus cosine over 1. So we have, again, a numerator. We have a denominator. I'm going to go ahead and continue to just work in the numerator. So in the numerator, I'm going to find the common denominator of 1 and cosine, which hopefully makes sense that it's a cosine. So if I'm just looking at the numerator and making a denominator of cosine, then the 1 is going to stay a 1. I'm going to have to multiply this by cos over cos, which gives me 1 minus cos over cosine. Still a big division bar. And then in the bottom, I still have 1 minus cos over 1. Whenever you have a complex fraction like this, try to find a common denominator in the top. Did that. Find a common denominator in the bottom. Did that. So now you're going to go ahead and do the keep change flip. So the keep change flip, remember, you're going to go ahead and leave the numerator, 1 minus the cosine of theta over the cosine theta. You're going to change the big division into a multiplication. And then you're going to flip the bottom to be 1 minus cosine of theta. Remember that these binomials have to come, they have to stick together. You can now, of course, cancel this 1 minus cos from the numerator with the 1 minus cos in the denominator, which is going to leave you with a 1 over cos. And what do you know? 1 over cos is in fact equal to a secant. So as long as you get that left-hand side equal to the right-hand side, that is your goal. And again, we've seen complex fractions, we've seen common denominators. Maybe we haven't seen too many of them all in one problem. Again, nothing is brand new for today. It's really just working your algebra bone and making sure that you know how to get the problem started more so than anything else. One final problem to go here. So take a look over on the left-hand side. This entire thing is the left-hand side, including that -1. So you have a whole lot going on, which again simplifies to just be this nice, lonely little secant. Again, the only way you can take the big old mess from the left and get it to be equal to the right is if lots of things cancel. So there's a couple different maneuvers that you could do to get started here. I'm actually going to start by finding a common denominator. So remember that this 1 minus cosine, those have to stay together. So adding parentheses might be helpful. Then I'm going to go ahead and remind myself that this is 1 over 1. So the common denominator that I want here is 1 minus sine. When I take this first expression and if I leave it as 1 minus sine, then this is still going to be cosine theta times cotangent theta. And then as I've been trying to kind of get you ready a bunch of times now, because of the fact that this is a subtraction, when you go ahead and multiply this second expression by 1 minus sign over 1 minus sign, you have to make sure that you distribute that minus. If you don't, things are not going to cancel, and then you're going to kind of be dead in the water. So from here, I'm actually going to try to do a couple of things at once. I'm going to go ahead and just work in the numerator for now. So everything that I do is still going to be happening over this 1 minus sine of theta. So I'm going to take the cosine of theta that I currently have, and I'm going to put that over 1. And then I'm going to take this cotangent, and I'm going to write that as cosine over sine. Then I'm going to distribute this negative. So this is going to become a minus 1 and then a positive sine theta. So then from here, again, just looking at the numerator still, that's really all I'm focusing on at the moment. I'm going to go ahead and continue to leave the denominator as 1 minus sine. So if I multiply this, I'm going to get a cosine squared of theta over sine minus 1 plus sine theta. Again, you have some fractions in the numerator, but not everybody. So I want to turn everybody into a fraction. So I'm going to rewrite this as 1 over 1 and then sine over 1. Again, I'm still going to focus on my numerator. So denominator stays 1 minus sine. The common denominator of this sine and this 1 is just a sine. So I'm now going to put everybody from the numerator over sine. So the cosine squared is going to stay a cosine squared. Then I have to multiply this middle term by sine over sine. So that's going to give me a minus sine. Then I have to multiply this third expression times sine over sine, which is going to give me a sine squared. I think I've used the expression a couple times now, but this is what I would actually call a hidden identity, because even though they are not right next to each other, you could rearrange them so that the sine squared and the cosine squared were next to each other. And if you do that, that makes a 1. So now in the numerator, that's going to give me 1 minus sine of theta all over sine of theta. This is still over 1 minus sine of theta. And again, when you have fractions in the top and fractions on the bottom, this is a big old complex fraction. But your salvation usually relies in the keep, change, flip. So if you go ahead and do that, you're going to get 1 minus sine over sine times 1 over 1 minus sine. And then would you look at that? This 1 minus sine cancels out with this 1 minus sine. You're going to be left with 1 minus sine. And that is, of course, equal to the cosecant, which is exactly what I told you it was equal to. So that's how you know that the problem is now over. So again, if you want a big messy thing to turn into a nice small thing, the only way that that is going to happen is if a lot of things cancel, and the very best way to get things to cancel, is by using the common denominators and the keep, change, flip. So because this was a video on the shorter side and you're watching it for homework, you should now spend some time either starting homework 57 if you are all caught up to date. Yes, we're going to work on it tomorrow in class, but because it was a short video, go ahead and get a jump on it. Or if you're behind on any homeworks, 55 or 56, go back and work on that. So thanks very much for tuning in, guys, and we will catch you next time.